Okay, hello everybody. So, we continue with our discussions on the flow regimes which were set. Yesterday I had just mentioned to you that when we first we identify the flow patterns and then we try to we try to depict the range of existence of the different flow patterns on a flow pattern map. And as I had mentioned yesterday, several different coordinates have been adopted for the flow pattern maps in macro systems. And then finally people have found out that no one pair of coordinate axis was suitable to predict all the transitions. So, therefore, what was adopted was that the most commonly adopted axis for your depicting flow pattern maps are the superficial velocities of the two phases. Now, let us see what happens for mini channels and micro channels. As I have mentioned yesterday, that we will be focusing on micro channels, but we will be also covering certain interesting aspects of the mini channels as well. So, in mini channels what do we see is that, just to recall, yesterday we found out that more or less morphologically the different flow patterns in mini channels and macro systems are similar. We find bubbly, slug, churn, slug annular and annular flow patterns, keeping in mind that the slug flow occurs over the largest range of flow velocity, and naturally depending upon the appearance of the slug flow, they are referred to as capillary slug, plug, bubble train. All of them they refer to the intermittent periodic flow pattern, which is commonly known as slug flow. And usually in slug flow we find that the liquid slugs are unaerated. So, therefore, it comprises of one two-phase region comprising of a Taylor bubble and the countercurrent falling liquid film or the adjoining liquid film, and an unaerated pure liquid slug. The other thing which we should remember is that churn flow pattern, as we observe in macro systems, do not exist in micro systems, quite naturally because of the increasing influence of surface tension or surface forces. Several different phenomena which mark the transition between the slug and the annular flow patterns are termed as the churn flow patterns. And well, the other thing which we should remember, that stratified flow distribution has not been reported even for milli channels. Now, with this in mind, again we find that the most commonly used flow pattern maps, they use the superficial velocities of the gas and liquid as the two axes, and if it is liquid flow, then we use the discontinuous at the lighter liquid superficial velocity in the y axis, in the x axis, and the heavier liquid superficial velocity in the y axis. For example, suppose it is water toluene flow, then in that case water flow rate is the y axis and toluene flow rate is the x axis, and the flow pattern maps are depicted as shown. These two maps, they have been developed in our laboratory, and for gas liquid downflow in vertical pipes. And this is also a three-dimensional flow pattern map that we had tried to develop just in order to show the coupled effect of liquid velocity, gas velocity and pipe diameter. So, from here if you observe closely, it gives you a lot of information. For example, it tells you that more or less at high liquid constant gas velocity, we find that for low pipe diameters 2.5 millimeters, it is more or less plug flow, and as we come to lower and lower liquid velocities, the situation it becomes elongated plug or plug flow, whatever you say. Now, as we increase the diameter, we find that the tendency of plugging decreases, and in the 12 millimeters we have a dispersed pattern in contrast to the plug flow pattern which we had observed here. Same thing is noted for moderate or medium liquid velocities. In this case also we find that the well defined plug flow becomes deformed plug flow, and then we get something like a plug annular or slug annular transition, and as we come to still lower liquid velocities, we find that there is falling film flow or the annular flow pattern as it is called, and the interface of the falling film is much smoother in the 2.5 millimeters as compared to the 12 millimeters. Same thing if we see the variation of your gas velocity and diameter, we observe a similar trend. The existence of the larger proportion of existence of slug flow in the smaller diameter pipe and the lesser proportion of existence of slug flow in the larger diameter pipes. And this particular situation, this shows the typical flow pattern map which we are used to seeing in a fixed diameter of 10 millimeters. So, here we have tried to capture the effect of phase velocities and diameter for one particular set of air and water velocities, expecting that it is going to give us much more information. Now, we come to the microchannel part. Well, in microchannel it was very evident that there was a predominance of slug flow pattern. Just to summarize the reasons, or just in a nutshell, I would just like to mention the reasons which dominated periodic slug flow in, or rather which led to the dominance of slug flow pattern in microchannels. And just as we all of us know that the surface tension was dominant compared to body forces, and also your viscous forces were much dominant compared to inertial forces. So, therefore, if you just in a nutshell, if you observe, the first thing is that since the Reynolds number was very low, so naturally for most of the situations we had encountered laminar flow of the liquid. As a result, the liquid did not have sufficient inertia to break the gas slugs into smaller bubbles at even at high liquid flow rates also. Okay. So, therefore, the bubbles, once they formed as slug flow, they did not have the tendency to shear and form the bubbly flow pattern. Next, even if you go for higher liquid flow rates also, what happened when we went for higher liquid flow rates? It caused a larger pressure drop, and when the gas was trying to flow through this larger pressure drop, it had a tendency to expand and accelerate through the liquid. So, naturally, even if it was sheared to smaller bubbles, they were flowing very fast and coalescing with one another to forming and form the elongated plug flow pattern. On the other hand, if we find that at higher gas velocities, what happened? There was increased waviness in the liquid film. When there was increased waviness in the liquid film, naturally the amplitude of the wave was sufficient in order to bridge the continuous gas core, and therefore, the existence of annular flow was much difficult as compared to larger tubes. Again, at higher gas velocities, what we found was the gas slugs, they were coalescing to form a semi-continuous gas core, okay, where the gas slugs, they were separated by short liquid plugs. So, therefore, this gave rise to the semi-annular flow pattern, but the annular flow pattern with a continuous gas core was absent. So, therefore, we find that the plug flow, it was favored both at high liquid velocities as well as at high gas velocities. Thus, plug flow had obtained a dominance over both the bubbly flow pattern at one end as well as the annular flow pattern at the other end, both being inertia dominant flow patterns. Another unique feature which we observed for microchannels was the existence of liquid ring flow, and this also we had discussed already. The interfacial waves in this particular case, they were regularly spaced and of larger amplitude as compared to the diameter of the channel. Naturally, the relative amplitude was quite high. So, therefore, the waves, they looked symmetric rather than leaning in the direction of flow. So, therefore, they gave the appearance of a liquid ring flow, which was unique to microchannels, and this was not observed for mini channels or for larger channels for that matter. Now, when we go to, or rather when people try to plot the range of existence of the different flow patterns in microchannels, what people observed were that the main characteristic feature of microchannel was the simultaneous occurrence of multiple flow patterns for the same flow conditions. Or in other words, even if we keep the gas velocity, liquid velocity and everything else constant, if we observe the flow through the channel, then we find that different flow patterns appear at the same location at different times. So, naturally then how to identify what is the exact flow pattern or how to denote the flow patterns on a flow pattern map. So, accordingly Kawahara, one particular group, and Chung et al., what they did, they went on examining the flow patterns for a sufficient period of time, and then they examined the time fraction of the different flow patterns, or rather the time fraction of existence of the different flow patterns for each flow condition at the observation window. They had an observation window, they were observing there, and maybe they were observing for say 5 minutes. Out of the 5 minutes, they found for different time instants slug flow was occurring, and maybe the total time of existence of slug flow was say 4 minutes. For the other 1 minute, some other flow patterns were existing, including single phase liquid flow and single phase gas flow. So, accordingly what they did, they plotted, or rather they tried to identify the probability of existence of the different flow patterns along with the time averaged void fractions. For example, if the void fraction is very large, and if the probability of appearance of say slug, liquid ring and annular, they are more or less comparable, and alpha is much greater than 0.8, then in that case it was denoted as annular flow pattern. For moderate void fractions, naturally it always happens that slug flow occurs over a large range, and so it was slug flow pattern. In this way, the probability of existence of any particular flow pattern was studied, and the highest probability flow pattern was taken as the dominant flow pattern under the specified flow conditions. So, in this way the flow patterns were identified and the flow pattern maps were made. In this case also we find that the commonly used axes are the superficial velocities of the gas as the abscissa and the liquid as the ordinate. And one thing I would like to say is that in this particular case, it is not the inlet velocity of the fluids. Now, for large diameter pipes, the superficial velocity and the inlet velocities are the same. We do not differentiate between the two. Why? Inlet velocity is the velocity which is measured by the flow measurement device, which is there upstream to the test section. We measure the flow rate there, maybe in LPM, either the mass flow rate or the volume flow rate, and then we just divide it by the cross sectional area and we get the inlet velocity. And the superficial velocity is defined as the velocity which the fluid will have if it were flowing alone in the pipe. Quite naturally, it will be having this particular velocity only. So, therefore, the superficial velocity is commonly taken as the inlet velocity for macro systems. Now, in this particular case, there is a very large pressure drop, as I have already mentioned. So, naturally, the superficial velocity should be the velocity which the fluid will have if it were flowing alone in the conduit, true, but at the condition at which it is flowing now. So, naturally, it is now flowing at that particular location at a pressure which is not equal to the inlet pressure. So, therefore, the superficial velocity, it is calculated by evaluating the properties of the two fluids at the pressure in the observation window. And in this case, it is assumed that the pressure varies linearly from the inlet to the outlet of the channel. Accordingly, the pressure in the observation window is evaluated and the superficial velocity is calculated accordingly, and then we have the typical plot of say JL versus JG, or in what, if you wish to write it as the superficial liquid velocity to the superficial gas velocity, whatever you wish. In any of these they are plotted, and usually the flow pattern maps are depicted. But in this case, you know that majority, the main portion of the flow pattern map is occupied by the slug flow pattern. So, naturally, there is not much information to be gathered from these flow pattern maps. Now, people have also observed that there is a remarkable influence of phase physical properties on the flow pattern boundaries observed. So, in order to capture this particular dependence, very frequently some non-dimensional groups have been adopted. Out of the commonly known non-dimensional groups that have been adopted, we find that the Weber number of the gas, the superficial Weber number of the gas versus the superficial Weber number of the liquid is very frequently used as an alternate to the superficial velocity. Well, so with this, more or less I have given you an idea regarding the basics of the flow patterns in a microchannel, the flow pattern maps. Now, I would want to discuss one particular analytical model based on basic physics which we had developed in the multiphase flow laboratory to predict the liquid-liquid flow patterns in reduced dimensions. We have used it for liquid-liquid flow, but it's more or less general and it can be used for gas-liquid flow in reduced dimensions as well. This model I would like to discuss because this is quite versatile. The thing is, it can predict the range of existence of the different flow patterns, number one. Number two, it can do this for both horizontal and inclined pipes. And thirdly, it has been modeled in such a way that it can also identify the range of existence of the mesoscale between the macro and the micro domain. And most importantly, we find that usually whatever analytical models have been developed for predicting the flow pattern transitions, all of them, they predict the transitions as occurring at one fixed particular location. But in reality, we find that the transitions, they occur over a range of conditions, or in other words, in a flow pattern map, the transitions should be depicted as a curve, as a zone or a region rather than a unique curve. While most of the analytical models, they show transitions as a unique curve. This is also taken care of in this particular model, and this actually predicts zones of transitions between the different flow patterns. Now, this has been based, as I have told you, on fundamental physics, and this is based on the principle of energy minimization, which states that quite naturally all of us know the conservation of energy, which states that under steady state conditions, the total energy holdup of the system, or in other words, the total energy content of the system per unit volume should be minimum for the stable flow patterns. So, what we do? We try to estimate or evaluate the total energy content of the system, that is a two-phase flowing system, per unit volume for different flow patterns, and then we try to draw curves of the total energy versus the void fraction, and then we find that for each void fraction, the one particular flow pattern will have the minimum total energy, and we postulate that that particular flow pattern is the stable flow pattern under the set conditions. When we change the conditions, it can be change of pipe diameter, it can be change of fluid velocities, it can also be change of fluid properties. Then we go to a different set of conditions. Under that conditions, again we evaluate the energy terms, and then we find out what is the minimum energy under the changed condition. It can happen that if the conditions have not changed much, the same flow pattern continues to exist. If the conditions are changed to a large extent, then we might get a different flow pattern under the changed condition. Now, how do we go about? The first thing, we have developed this model for reduced dimensions. So, accordingly, what do we postulate? We postulate that the total energy, it is a summation of, definitely kinetic energy is going to be there. It is there also in macro systems also. Then we should have a gravitational energy term, which will be gradually reducing in importance as the channel dimension gets reduced, and along with this there should be a surface energy term, rather it is not gravitational, I'll write it down as potential energy term, and along with that there should also be a surface energy term due to the surface energies at the liquid-liquid as well as the solid-liquid interface. So, therefore, we write down the total energy in terms of the total energy change for, or rather the total energy, the energy, kinetic energy change, the potential energy change and the surface energy change. And each of these changes, they are evaluated in, they have to be evaluated with respect to some particular standard. The standard which is taken in this particular case, it is the kinetic energy of the two phase flow minus the kinetic energy reference, which is the kinetic energy of water flowing at the total mixture velocity. So, therefore, this has been considered in this particular case. Okay. So, accordingly what has been done? Accordingly, the kinetic energy term, it has been written down as delta E k E for the pattern minus delta k E for the reference system, where the delta E k E 0 for the reference, this is taken as pi d square L rho 1 u1 plus u2 whole square divided by 8. So, you can see this is nothing, this is just the kinetic energy of water flowing at the total mixture velocity u1 plus u2. So, therefore, the kinetic energy of that water. So, therefore, the total energy, rather the kinetic energy change is taken with, this is no delta, is taken with reference to the kinetic energy of water flowing at the mixture velocity. In the same way, the potential energy term, it is taken as your potential energy for any set pattern, whatever pattern we consider, minus the potential energy for the reference state, where the potential energy for the reference state, it is given as the potential energy of water occupies the entire pi. And again, if we take surface energy, it is again the same thing. This will also be given with respect to the surface energy of the particular pattern minus the surface energy of the reference substance, which is again water flowing at the occupying the entire cross sectional energy, which is nothing but the surface tension of water. Okay. And finally, the total energy for any particular pattern, the total energy change for any particular pattern in non-dimensional form, it is given as the delta P E for that pattern plus delta kinetic energy for that pattern plus surface energy for that pattern. So, in this way we formulate it, we develop expressions for steady state total energy. We postulate that the total energy terms under steady state conditions for per unit volume of the conduit, which has specified geometry and orientation. And the postulations are based, or rather they are primarily applicable to low diameter conduits, where we find that the instabilities due to turbulent stresses and Kelvin-Helmont step instabilities are negligible compared to surface energy induced instabilities. So, therefore, there are two things which are taken care of here. One is that we are doing it for low conduit diameters, where we can very well assume that the hydrodynamic interfacial processes governed by Taylor instability do not apply to conduit dimensions equal to or less than the Laplace length scale, right. So, therefore, this is number 1. So, therefore, the analysis is concentrated to low diameter pipes. The other thing is we have been working on low to moderate flow rates such that the kinetic energy term does not become very dominant as compared to the surface energy and the surface energy term. So, we would like to operate in the surface energy dominant condition for low to moderate pipe diameters, and so accordingly naturally we do not consider the dispersed flow pattern in our case, since that occurs at high liquid velocity where kinetic energy is dominating. So, therefore, this analysis is concentrated for the plug, the annular and the stratified flow patterns. Just like all analysis, in this case also we have assumed two things. One is the idealized flow, that is a fully developed steady state flow, and a smooth liquid-liquid interface. Now, this is quite relevant for micro and milli systems, because as we have observed earlier also we have seen that more or less the interfaces are smooth due to the pronounced influence of viscous forces here. And the other thing that we have introduced a slip here by assuming that the inlet and the in situ velocities are not the same, or in other words, as I have written down there, the in situ composition is not equal to the inlet composition. So, on this particular basis the analysis has been developed, and accordingly, so as I have told you that we have considered a flow of an aqueous phase and an organic phase in this particular case through a horizontal conduit of length L and diameter D, and they are considered with respect to the corresponding reference values for flow of only water, and this particular work has come out in the paper, which you can refer for your for further understanding of the work. And the equations have been developed based on the geometrical or rather geometrical morphology of the different flow types, as has been shown in this particular figure. So, in the next lecture we continue with developing the model and the interesting results which the model shows us or gives us regarding two-phase flow in microchannels under surface tension dominant conditions. Thank you very much.